Hello, ladies and gentlemen. Today, we're going to study the Fourier transform infrared spectrophotometer, referencing the Wikipedia article on FTIR. Here's a picture of a Michelson interferometer. It takes light from a coherent source. Coherent being, you can see that wiggly shape going horizontally. The fact that you have this wiggly shape, which can then bounce off this partially silvered piece of glass, which splits the beam, or it's a beam splitter. Part of it goes up, hits a mirror, and comes back down. Part of it goes straight, hits a mirror, which is on a track, so it can move. Hits that beam splitter again and bounces back down, recombining. Now, if the distance to the upper mirror and the distance to bounce off the movable mirror is exactly the same, then it's a zero difference. And when those waves come back together, since they've traveled the exact same distance, they're going to recombine in a constructive way, constructive interference. And so you see the recombined wave is a single wave going downward, which as part of the FTIR instrument, it goes through a sample, which then goes on to the detector. Now, the question to talk about is, well, before I do, let's go study one more thing. As you move that mirror and get constructive and destructive interference, you'll get a raw data output from the detector, something like this. Now, the mirror movement we can see is on the horizontal axis in millimeters, and they got a 5 and a 6. So you can see right at the 0 spot is when you have the brightest or the tallest constructive, and then it falls down to the most destructive or darkest. And the baseline, where as we go out a few, a millimeter or two, this constructive and destructive interference vanishes pretty much, and you get this baseline, which is actually happening at a mid brightness, as opposed to the high brightness up top and the more dark down below. And in the range of 1/10 of a millimeter or less, you're gonna get the movement of 1/10 of a millimeter. You get the wide spike up and down. Now, this is a graph of interferences caused by moving this mirror. So you start left, move middle. Oops, did I lose it? You start left, let's say, move, you reach the 0 difference position, and then you keep on moving to create what we have here. We start left, you get this baseline where there's very little interference, and then the interference starts happening, reaches a maximum at the 0 difference spot, and then it starts decreasing the interference up and downs as you continue to move the mirror. This is a bunch of different frequencies. Now, what's shown here is just a single frequency from a so-called coherent source. A single frequency is just shown, going to create a single interference. Now, if a single frequency only was being, like a laser beam, was being broadcast and through this mirror apparatus, and the mirror was moving, what you would get over here would be, from the get-go, like if this was from a laser beam, you would get constructive and destructive interference as you scan the distance. But the reason why you don't get that, like what a laser beam would produce, is because of the whole idea of the source of light. Ideally, in a Michelson interferometer, you have a so-called coherent light source. But to create the light source for an infrared spectrophotometer, it's a heated bar of some material, and it's giving off black body style radiation. So black body style radiation would be just a moment here, ladies and gentlemen. Would be your emitter of radiation, a heated body which has some size, maybe a centimeter or something of that effect. Now, how can a black body have coherency in its radiation? The whole idea of black body radiation is if we went to one particular spot on its surface, the molecules bouncing around are bouncing in a Brownian motion Brownian motion pattern. In other words, a particular molecule is bumped rapidly, and it would emit a more rapid frequency of infrared radiation. The deal is, if you go to a different spot, it's bouncing around randomly. A bunch of different molecules are bouncing around, and they're going to be emitting, since they're bouncing differently, they're going to, if I did have a super powered oscilloscope with an electromagnetic detector, which we do not have, and we actually could graph the light electromagnetic radiation coming off, it would be a different graph from two different spots. Now, since one mathematical way to think about or analyze something that's giving off many different frequencies to create the end result of the wiggliness you see on your, for example, if we had an audio, we had a microphone and we picked up an audio and graphed it on an oscilloscope, the different frequencies in that audio would create the audio pressure wave sensed by the microphone to rise up, then rapidly zoom up, sometimes have a slow spot. It would be, the wiggle would be varied. Sometimes it would be bouncing rapidly, sometimes it would be slow. The slow, of course, corresponds to a lower note. So the notes of the light, if we think of it as notes in audio, okay, so two different spots, different graphs. And then what we're going to do is analyze each spot as a sum of different frequencies. So in that analysis, let's just look at one certain frequency only. Now, since they're coming from different spots, the phase, comparative phase, one could have its peak starting out at a certain time, and the other can have the peak being zero at the beginning, I would say at the get-go time. But what the question is how much distance do we have to move along the graph? Okay, if we had zero distance moved, of course, and recombined it at the zero distance spot, the difference is zero, then they would both combine and add together to create a more powerful signal shown on the scope. But the question may be, how far out would you have to go until the signal would be opposite? so it would have destructive interference. And it's a certain distance out based on the wavelength. So even though it's different phases, you're going to get that same distance out to create your first destructive interference happening. And you move a certain distance forward, and then they're going to both, at this particular frequency, are going to both construct again constructively. So even though it's an entirely different phase, as the mirror moves a certain distance, that for that particular frequency, in unison, they will both constructively interfere. If you move it some more, they'll both destructively interfere at the same distance out. This is as long as your mirrors are very well horizontal and vertical, and do not wibbly wobbly, so that the light from one spot on your emitter bounces and then recombines at a very certain spot, coming through space. And then let's take away the sample thing, right? But as it'll hit the sample, or if we take it away, it'll hit the detector at a certain spot. So light from one spot on our emitter compared to a second spot will be focused back together on the first and second spot on the detector. And those two spots, even though it's different, a different wave, they're going to combine constructively and destructively as you move the mirror at the same amount of movement for a certain frequency. So it's as if everything was coherent if you keep the spots happening. Oops, did I mess up? Yeah, so black body can be coherent as long as each individual spot on the emitted surface is kept together, so that when it recombines back on through this mirror and semi-silvered mirror or glass surface, it's recombined so that one spot is recombined back together with that one spot. Now the size of wavelengths of infrared ranges from about 1/500th or about 2 micrometers, which is 1/500th of a millimeter, up to about a millimeter, or maybe even a tenth, let's say up to a 10th or 20th of a millimeter. But that size, if we think about, let's say, a 64 megapixel camera that has a 1 inch by 1 inch detector, that would split the surface into 8,000 pixels on horizontal, 8,000 steps horizontally by 8,000 steps vertically. So 8,000 times 8,000 creates 64 million pixels. So you can see the state of the art of cameras and lenses and mirrors can definitdefinitely handle a 64 megapixel camera in terms of refocusing all that light into a dot that's 1/8,000th of an inch. So if we divide that by about 22 or 25.4 millimeters per inch, let's just round that up to 20. So 8,000 divided by 10 is 800, divided by 2 is 400. So about 400 dots per inch is this range we're dealing with for the shorter end of the infrared spectrum. Happens to match with our state-of-the-art of optics. So in other words, you don't see too many FT visible instruments, because the wavelength of visible light is just into a range that's kind of out of our reach in terms of, moving a mirror. The amount of movement here would just be too small. You go through too much wavelengths to get what you see here. So in the infrared, this is a movement of about 1/10 of a millimeter, that center part with the greatest interference going up and back down into the darkness. So in other words, so we have to keep these mirrors. If the instrument is actually built in this the very simplest to understand Michelson interferometer, the verticalness of this moving mirror has to remain without any wibbly wobbly as it moves, in order to keep all the spots on the black body emitter recombined. So the single spot would then be recombined at a certain spot on the detector. And we've just talked about how, even though it's different actual wave, the frequencies will all constructively and destructively interfere with the same amount of movement. So across the detector, you're going to get all the light from a certain frequency get bright across the entire detector, even though it's from different spots and different actual electromagnetic radiation graph and different phases. They'll all get bright and dim at the same time across your detector, as if it was all coherent, because you're keeping that mirror very precisely vertical, so all the spots so the spots remain combined. So if any tilt does happen, you will lose this effect as seen in this thing. You will lose the constructive and destructive interference. Now, as you go through many wavelengths of distance for the infrared light, you can see the constructive and destructive interference after about going from 5 to 6 millimeters. Only after about, let's say, 1/4 millimeter or 1/3 of a millimeter, you no longer get much at all of the constructive and destructive interference, because of the limits of our ability to move that mirror totally vertically, or totally unwibbly, no wibbly wobbly going on with that mirror movements in the infrared light. So, ladies and gentlemen, as described in our Wikipedia article, you do the Fourier transform on this raw data here, and it will show that it's a sum of a bunch of different frequencies. Now, the reason why this is in the realm of our electronics is because as we're moving that mirror slowly, it's like going up and down, under, in the range of, let's say, the ability of our electronics, if this is audio, then let's say 20,000 ups and downs per second is well within the grasp of an analog to digital converter collecting this data, and then using a computer to do the Fourier transform on it to turn it into a frequency graph. That's what you see, like instead of distance here and time and then movement going forward, it would have a graph of a lower frequency as you go to a higher frequency, and then the various frequencies, which of course are very, in the terahertz and gigahertz range, which are well or easily beyond the grasp of most electronics. But you can at least get it from this data. because the movement of the mirror is related to the size of the wavelength, which is 1/500th of a millimeter. And if you move it at 1 millimeter per second, that's 500 interferences and destructive, constructive and destructive. So it's similar to a 500 hertz tone. Now there may be, I get mixed up on this, but it may be a doubling of 1,000 hertz tone because you got both the constructive and destructive happening. But it's all well within the audio frequency style electronics to collect data and then turn this into a frequency graph. But of course you're going to display it related to the wavelength of light in terms of micrometers, or you can just go ahead and turn into the frequency of light, which is terahertz or gigahertz. Alright, I think I bored you all stiff. Thanks for listening, and I hope we cleared up the question of how a black body radiator can be considered a coherent wave source. Thanks again. Bye.